Welcome everybody to this session about lessons that we learned from deploying machine learning in the wild. And by the wild, I mean the good old industry of cement and concrete. I'm Robert Meyer, CTO and co-founder of Alcemy. So what do we want to talk about today? So first I want to start with the big and massive problem that the industry of cement and concrete has. What kind of solution, particularly what kind of machine learning solution we deploy in order to help solving that problem. And then the major part will be about the lessons that we draw from running these solutions in actual cement plants. So what is this big problem that I'm talking about? Well, concrete is the most used building material across the planet. And it's just gonna get bigger. So it's expected that the world building stock will double by 2060. That means from now until then, we'll be building the equivalent of New York City every month. And that's great on one side because that means more housing and more infrastructure for a still growing and emerging world. But on the other hand, that comes with a heavy price tag. And that price tag is the carbon emissions of that supply chain and the carbon emissions of cement and concrete, while that are emitted because of creating this massive building stock. Because if cement and concrete was a country, it would be the third largest emitter, right after China and the United States. So where do these emissions come from? So if we look simply into the supply chain and how concrete's made, it all starts with a quarry. And that is a limestone quarry, to be precise. And that's great because limestone is abundantly available in the Earth's crust, meaning it's available in these huge quantities that we need to actually build the world. Sorry. Then this limestone is taken to a cement plant where it's refined in the plant to the cement. This is this gray powder. Then this gray powder is further shipped into concrete batching plants, and there it's finally turned into concrete, adding water, sand, and gravel, and some admixtures potentially. Then you can see these concrete mixing trucks that transport this still liquid concrete to the construction site, where it then can be poured to build bridges, houses, infrastructure, you name it. So, and this supply chain has a massive carbon footprint. And if you want to get an idea where this carbon is actually coming from, or these emissions are coming from, then basically the vast majority of the carbon emissions are happening here in the cement plant, and there in one particular processing step. And that is a rotating kiln. So where we take the limestone or the ground limestone and burn it to what is called clinker. And what happens is in that process is that the limestone from the Earth's crust, basically the CO2 that was bound in the limestone millions and billions of years ago, gets removed in this chemical reaction out of the limestone and blasted into the air. So these emissions are like process inherent, right? So even if we find ways, for example, to heat the kiln with renewable energy, we would still have the CO2 emissions coming out of the limestone. You can think of it as some sort of fossil fuel. So if renewable energy isn't a solution here, what is something we can do about these massive emissions of this building material? So one rather straightforward solution, and the one that we're proposing and that we're hoping that our technology can help scale up more, is rather dull and relatively straightforward. And it goes as follows. So if this is regular concrete with like a little bit of water, a little bit of admixtures, sand, gravel, and then regular cement, and if we take a closer look into cement is basically made out of two things. So one is the clinker, so that's coming out of the rotating kiln, that's the one with the heavy carbon footprint, and so-called supplementary cementitious materials. That can be all sorts of things, all sorts of filler material, such as slag or CO2, quote-unquote, free materials, such as, for example, just ground limestone. And so the idea is the following. So if the clinker, because being burnt limestone, where the CO2 was removed out of the limestone, is so CO2 heavy, then let's simply try to optimize or scale down the recipes in the sense of using less clinker and more CO2-free filler materials. So if that, again, is regular concrete with regular cement and loads of clinker, then you can slash the carbon footprint of that material without sacrificing like a lot of its properties, but having a concrete that is similar in behavior, simply as following. We can use low carbon cement, so we need a little bit less of water and a little bit more admixtures, but we basically want to replace the clinker with more filler material. And with that simple step, as I said, you can slash the carbon footprint by up to 60%. And this isn't something that we invented as a company, or that is new knowledge that has been in the literature and knowledge in the cement and concrete industries for years. And we've have helped already deploy such cements and concretes in the wilds. So we've supported a lot of recipes that were tested in laboratories and even deployed on real construction sites. So for example, in Berlin, the Edge East Side towers, top 2 floors were built with such kind of cement and concrete. Sorry. And that's not something that basically our company develops. This is something that we helped our customers developing themselves. So, which is great, which is cool. So these low carbon recipes exist. They can already be deployed these days in the wild. You can use that to build real skyscrapers. That's great. So you might ask, okay, that's super. Why do you need a machine learning company to actually do that? So, and the reason is as follows. As I said, the goal that we have as a company is to propose our customers, cement and concrete companies, to reduce the clinker content in their cements and concretes respectively. So we want to reduce clinker. But the caveat of this is usually because you took out the binder material and replaced it with usually basically some filler material, what you get in the end is actually a bit less robust concrete. So that means, in a sense, that basically problems that you have during your production process get amplified by your concrete mix designs. So, for example, the most important property of cement and concrete is its compressive strength, right? So that keeps the buildings stand upright. So let's say you see here the time of production and different batches over time that were produced of cement. And because cement is a very heterogeneous material in the sense that its raw material, limestone, and the chemical and mineralogical composition can differ from cubic meter to cubic meter in the composition. This manifests itself also variations in the properties of the cement. So, for example, the actual strength that a cement develops when it's turned into concrete might vary from production batch to production batch. And this is what you can see here. In these low carbon recipes, because you have less robust concrete, what will happen is that even fluctuations already of the cement strength get amplified later in the concrete strength. So any errors that you make, let's say you produce a low carbon cement that is supposed to have like 50 megapascal strength on average, but it shows huge variation already during the times of production. If you then form concrete recipes with low water in it, this actually gets amplified. So one of the major prerequisites for these low carbon recipes to actually scale in industrial scales, so that you can apply them not just on like particular well observed construction site, but really scale this to many construction site and many concrete plants, you need stable cement strength in the first place. So basically, if I order a low carbon cement that is supposed to have 50 megapascals compressive strength, then it should be very close to 50 and not have like 55 or 45 megapascals, because again, that problem might get amplified later on in my concrete mix design. But this is actually fairly difficult to pull off because the cement strength is hard to measure. Because measuring strength, I mean, cement is a powder, so measuring its strength actually requires you to form a cement prism or a concrete cube and let it harden for 28 days. And then you take that cube and you crush it. And then you only know its real strength, its real compressive strength. And this is basically how you do it. So you have this concrete cube that you put in a press, and then you apply pressure, and eventually it will break. Then you know the exact compressive strength of that cement or concrete. So what we do is we use machine learning to get this cement strength on point. So if you have a low carbon cement that is supposed to deliver 50 megapascals when turned into a concrete cube, that it actually does so and not deliver like 45, which would be bad, or 55, which probably means there's some over design. And we do this by shortcutting the time that you need in order to figure out what the strength is going to be. So instead of having to wait 28 days for the real results, we use machine learning to predict this 28-day strength at the time of production so you can react immediately. So here's how that works. So as I said, at the time of production, there is cement being produced. And because cement is made from limestone, which is very heterogeneous, you have these fluctuations in the compressive strength from different production batches. And this yields then these fluctuations in the compressive strength. And the idea is, can we counterbalance these fluctuations stemming from the mineralogical composition and the chemical composition of limestone with something that is under our control? And the answer is yes. Because not only the chemical and mineralogical composition of the limestone have an influence on the strength, but also the fineness of the material. So the more fine you grind your cement, the more stronger it gets. So basically, we are trying to find finest setups for this cement that counterbalance fluctuations from the chemical mineralogical composition. So that in the end, you get something that has a reliable compressive strength. So here's how that goes. So this is the last production step of cement manufacturing. So this is the cement mill where you take your raw materials such as clinker or supplementary cementitious materials like slag and fine limestone. You combine them, put them into the cement mill, and then grind them very, very finely. So then the fine material is basically coming out of your mill. There's a separator or filter step where you separate fine materials from coarse ones, and the coarse ones have to take extra truths through the cement mill. And you can adjust this separator to really influence the final fineness of the material that then ends up in your delivery silo as finished cement. Sorry. And at this loop, at particular points in time, there are samples taken. Actual cement samples from your finished materials. And these cement samples are taken usually at the silo and right after the mill when it's finished cement and when it's going into the silo. And these cement samples are automatically usually analyzed in cement laboratories. So for example, they use machinery such as X-ray diffractomy, X-ray fluorescence, or a particle size analyzer. And this gives you really the full picture of the cement sample in terms of mineralogy, chemistry, and the distribution of particle sizes. What it doesn't give you, of course, is the strength, because there's also strength tests happening, but these take 28 days to finish. So we take this laboratory data, XRD, XRF, and PSD, export this into the clouds, run a prediction algorithm that basically takes this data and then makes a prediction based on the mineralogical chemical composition and the particle size distribution to make a prediction of the resulting 28-day strength of that material in case you would take that, form a concrete cube, and let it sit and harden for 28 days and crush it. And if that strength, for example, is over target, let's say you want 50 megapascal, but it's 53, then we can compute optimal fineness set points. So basically, you have a little bit too strong material, meaning you can grind a little bit more coarsely, and we feed that back into the plant. So either directly into the expert system of the mill, so this is like a complete automated loop, or as a web application for cement mill operators so they can adjust the fineness. And this loop then basically runs 24/7 in a cement plant. And with that, we can really make sure that strength has less fluctuations. And this is how this data looks like in reality. So basically, you can think of it as a giant Excel sheets of all their laboratory data. There is our target, so the real compressive strength tests that are still being made. That's the one that take usually 28 days, because you have to form this concrete cube, let it sit in harden for 28 days, and then crush it. And then we have our input data. So for example, this reflects the particle size distribution. This is the chemical composition, and this is the mineralogical composition. And then we can use this data to train a machine learning algorithm, and then use that machine learning algorithm and basically run this loop 24/7 and help improve the strength quality. And this is what you can see here, what then happens. So you can see here a lot of fluctuations in cement strength. So each black dot here really corresponds to one of these measures where these concrete cubes were formed and then crushed. And then we applied our algorithm, and we can see that we basically reduce these fluctuations by 30%-ish. And this already can help. This improvement of the standard deviation of the strength measurements of like 20-30% can already mean like $500,000 in savings. And this can be from a wide variety of things. So one, you have higher quality, you can get higher prices, you can reduce your clinker content, or you can save on grinding energy. So this is basically what's applied now in the wild. This is now in more than 20 cement plants worldwide. And here is what we learned along the way, scaling that out into many, many different plants. Sorry. One of the things is, and that's from a machine learning and science perspective, data science perspective, a bit dull, because the first lesson is do not spend too much time on too complex models. Because, I mean, this is what you want to do as a machine learning engineer, as a data scientist. You want to build fancy models. And I mean, we did because it's fun, right? So we tried deep learning, why not? With PyTorch neural networks. We tried support vector machines, Gaussian processes, XGBoost, you name it. But all of these gave basically none to marginal improvements. Problem is they even fairly hard to understand. So especially when you have deep learning networks and you try to figure out if the network learns something meaningful, that is a really hard task in itself. So in the end, what is really deployed in pretty much any our customers' plans is something rather simple. So it's regularized linear regression plus a random forest on the residuals of this linear regression. And this has a lot of advantages. So first, linear regression is fairly easy to understand. So we can simply look at the coefficients of that linear model to see if that model learns something meaningful. So for example, because we use that in a causal relationship, right? So the model needs to pick up that basically fineness actually regulates the strength of the material. And you can simply check that by looking at the linear regression coefficients of the fineness features. So yeah, this is something you should learn. Fineness fosters strength, titanium dioxide reduces strength, or of course C3S, the clinker actually increases strength. These are kind of stuff that's easy to check then. So simpler models are always better. It's easier in real life settings. The second lesson we had to learn is realistic model evaluation is key. Because, I mean, what you want to do is when you deploy a machine learning model in the wild, you want to make sure that before you deploy it, you have a good understanding of its actual performance. Because there's nothing more embarrassing from a machine learning engineering perspective if you think your model is doing well on your training set, but then once you deploy it, its performance is abysmal because you made some big problems in actually estimating the performance of your model. Sorry. And one of the things you have to take into account when it comes to cement data is that what you can see here, each black dot corresponds to an actual strength test, and in red you can see the corresponding prediction. But what you can see here is basically you see this sort of sinusoidal behavior what means is that these samples are super highly correlated in time. That means the ordering of the samples does matter. And that means you can't simply apply random cross-validation, which a lot of people use for estimating model performance. So what you need to do is something called temporal cross-validation to avoid data leakage. And that means basically that you take a consecutive piece of data, train your model on it, and then you take that model to predict the following parts of the data. And even that wasn't enough for us because remember, the actual strength test take 28 days to harden. So we basically had to incorporate that into our measurement or evaluation framework. So basically we train on a piece of data, then we leave out 28 days of data, and then we actually predict data in our training set. And this is basically then done again and again and again to really estimate model performance. And then on these different validation falls combined, we have a good idea of the actual performance this model is going to have in this real life setting, steering actual cement. And that's very important to do it that way because this kind of cross-validation is a much better estimate of real-world performance in comparison to random cross-validation. Because if you would randomly partition our data and evaluate our model on it, because we would ignore the temporal correlation, we would overestimate the model performance by around 30%. This is how big this temporal correlation actually has an influence in our data. Next lesson is machine learning is only the tip of the iceberg. Because I mean, machine learning is all the cool stuff, all the cool models, but in fact, in an actual application that is deployed in the wild, this is just a very, very teeny tiny part. So this is from a famous paper, The Hidden Depth of Machine Learning Models or Machine Learning Systems. So if you consider your machine learning call, like your core, your heart of your application, the cool part, the one everybody wants to work on, then this is a tiny one because you need all of the other stuff around it. You need ways to actually deploy your models. You need data verification. You need feature extraction. You need a lot of configuration. I oftentimes joke we are not machine learning as a service, but configuration as a service. And yeah, so that's pretty big. So this is from the paper, and just analyzing our GitHub repositories, that is pretty much what is inside our machine learning for cement repositories. And you can see the model part is really a tiny part. And even there, this model part already contains all the pre-processing because, as I said, the model themselves, they're super easy. It's linear regression and random forest, but there's a lot of brain power that actually went into this about all the different pre-processing steps that are required to prepare the data. And you will need this because running machine learning on customer-provided data is actually very, very challenging. Because customer data that you aren't owning directly, but that is provided by customers can be, very hard to work with. Because, so especially, we try to move our customers to a setup where basically they have a laboratory information management systems that automatically transfers the data into our cloud. But this is usually a huge step already in the onboarding, and especially in emerging markets, we have customers that can only provide CSVs or Excel sheets, and that's the truth. So you have to deal with stuff like that, changes in date formats and data formats happens all the time. The good old point versus comma as a decimal separator can change almost unpredictably. And then there might be humans actually prettifying the data. Because, I mean, if you're working in a cement laboratory and your performance, the performance that you're measured by, that your boss judges you by, is the performance of the cement, you might actually be inclined to make the results look a bit better than they really are. Let's say you measure a strength that is too low. There are cases where this was corrected and slightly moved more to the desired target. If you do this in a machine learning setting, that's pretty bad because the machine learning model will simply eat up that data and think that is real and learn the wrong relationships. Then, of course, there's lots of stuff and data drift and concept drift that can happen because of because devices need recalibration. Because they might actually get clocked from the cement and need to be cleaned and then recalibrated. And that creates concept drift. Yes, so this can cause these huge data and concept drifts like this. You have here, I think that's XRD data, and without changing much of the material, you can see these jumps because what happened is that the device was recalibrated, but basically the material didn't change, right? Sorry. So it's really great what we learned. If you can be the governor of your own data source, that's really valuable if you deploy machine learning. And in Cement, we aren't, because we are reliant on the PSD, XRD, and XRF devices of our customers. So that means we do have high variations in our performance in our different machine learning models across customers. And the customers who are well versed in sampling data, preparing data, and measuring data have much better machine learning models, because crap in, crap out. And this is something, just as an outlook, we also do machine learning in concrete. But here, the difference is that the data that we use to do machine learning is actually coming from our own sensory devices. It's not that we build sensory devices, but we always buy the same sensors and apply them to concrete trucks all over the world. And this is always the same sensors. So there, it's much easier to actually pool data. This is also something that we've had to learn the hard way. Pooling data in Cement can be hard and usually not improves your models, because the calibrations of the devices like PSD, XRD, and XRF are usually differing a lot between different plants. So, final lesson, machine learning as a service or configuration as a service is not comparable really to software as a service. So machine learning as a service has slightly smaller profit margins than software as a service. Because first of all, there's no such thing as a minimal viable product in industrial machine learning that you're like used to in a venture capital setting from software companies, where basically you churn out something very simple that gets you from A to B, a skateboard, and then people love that because they weren't skateboarders anywhere before, and then this thing turns viral, and then the more users you can onboard, you iteratively improve your product. This is fairly difficult when it comes to industrial machine learning, because your minimum viable product is not a skateboard, but usually already you have to start with the bike, because your minimum viable product is not a machine learning model that lives inside a Jupyter notebook, but this is something, if you want to have like a minimal product, you need something that is deployed in some form of loop in a plant, meaning you need to get data out, feed it into the machine learning model, get data out of there, and feed it back into the plant before you actually are creating value with your customers. So with that, you already have this loop, and that requires also then a lot of monitoring and a lot of bells and whistles around just to make that happen. Then, of course, what doesn't work is basically just providing the software and then leaving customers alone, because they are not used to statistical products such as a machine learning product. So you need a lot of consulting and educating, because I mean, people are, for good reason, skeptical. There's a basically an algorithm that makes predictions that are steering industrial processes. So you will be faced with huge a lot amount of skepticism, and there's a lot of educating involved. That means one of the most important functions that we have in our company is something called customer success. So these are people who basically can connect the world between our machine learning engineers and our machine learning application and our customers. They know how to talk machine learning, and they know how to talk Cement, and can really help our customers to be successful with our application and use that to really get a return on investment. So thank you very much for listening in on this talk. So very quick wrap up. So concrete is responsible for about 8% of worldwide carbon emissions. But low carbon concrete exists. That's great. Can be already developed these days. We've shipped this to skyscrapers already, but it requires reliable cement strength. However, machine learning can get the strength on point. And we do this, and there's a lot of lessons that we picked up on the way. One is, if possible, avoid complex models. Simplicity is key. Evaluate your models very realistically. as much as possible. Machine learning is usually only the tip of the iceberg. The most important stuff is all the scaffolding around it. Customer data, if you're not the governor of your own data, can be really, really hard to handle because you expect everything and expect the worst. And machine learning as a service is not necessarily software as a service because you have to start usually bigger and you need a lot of hand-holding and a lot of education. Thank you very, very much.